So what if the rules that run our universe weren't set in stone? Today, we're going to dive into how scientists are actively upgrading the quantum rulebook, literally rewriting a chapter that's been the gold standard for almost a century. It's a huge question, right? Have we figured it all out? Are the laws of physics complete? Well, a really fascinating paper from 2022 argues not even close. In fact, it suggests we might be on the edge of a major upgrade to our understanding. All right, so before we can talk about the upgrade, we got to look at the original source code. For the past 100 years or so, the entire operating system of the quantum world has been run by one incredibly successful but also kind of quirky set of rules. And at the very heart of that rulebook, you've got the Schrödinger equation. It is the instruction manual for the quantum world. It tells us with stunning accuracy how things like electrons do what they do. I mean, so much of the tech we use every single day is built on this thing. But, and this is a big but, it seems like even this masterpiece has a few missing pages. And those missing pages, oh, they deal with the really weird stuff. The kind of stuff that famously made even Albert Einstein uneasy, prompting him to call it spooky action at a distance. You know, the authors of the paper we're digging into today, they just nail it with this quote. The fancy scientific term for all this spookiness is non-locality. And man, it just shatters our everyday ideas about how cause and effect are supposed to work. Okay, so this really breaks it down nicely. In our world, things are local. To move a baseball, you got to hit it with a bat. Simple, right? But the quantum world, it's non-local. Two particles can get linked or entangled, and an action on one particle can instantly, and I mean instantly, affect the other, even if it's on the other side of the galaxy. This mind-bending, instantaneous link is the real puzzle here, and it's something the classic Schrödinger equation doesn't really have a good explanation for on its own. So, okay, if your number one rulebook can't quite handle the weirdest, most fundamental thing about the system, well, then it's probably time to update the rules, right? And that is exactly what these physicists set out to do. And what's so cool is how they did it. They didn't just toss out the classic equation. No way. Instead, they sort of surgically enhanced it, adding two really powerful new ingredients. So let's break them down. Okay, first up, long-range kernel effects. I know, it's a mouthful, but all it really is a new rule they wrote into the math that says, hey, what happens here can be directly connected to what happens way over there. It's basically the math for non-locality, baking that spooky connection right into the DNA of the equation. All right, the second ingredient is just as cool. Position-dependent mass. This tackles a whole other real-world issue. See, out in empty space, an electron's mass is always the same, but squeeze it inside a material like a semiconductor chip, and suddenly its effective mass actually changes based on where it is. And that little detail, it's absolutely critical for designing all the electronics we rely on. So you put those two upgrades together, the spooky non-locality and the changing mass, and suddenly you have this brand new, supercharged quantum toolkit. The big question, of course, is, what can you actually do with it? Well, you know, when you've got a new hammer, you go looking for the toughest nails. And that's what the researchers did. They took their new equation and pointed it right at some of the gnarliest, most difficult puzzles in all of quantum mechanics. And get this, the results were really impressive. Their new equation was able to describe these super tricky systems in a new way. We're talking about things like the Pais-Uhlenbeck oscillator. That's a theoretical puzzle that has stumped physicists for decades. And they also took on relativistic quantum systems, you know, where things are moving at insane speeds close to the speed of light. And look, these aren't just brain teasers for physicists. Figuring this stuff out helps us build way more accurate models of how the universe works. And that's the key, right? This isn't just theory for a whiteboard. This kind of deep understanding, this is the foundation, the bedrock for all kinds of future tech. And here's a really concrete example of why this matters. One of the biggest takeaways from their work is a brand new, much more accurate way to calculate that effective mass of an electron we talked about earlier. So what? Well, knowing that number with pinpoint accuracy, that's the secret sauce for designing the next generation of everything. Faster computer chips, better solar panels, you name it. Okay, so let's zoom out. What does all this mean for the big picture? For me, this paper is just a perfect example of how science really works. It's not about finding one single final answer and then closing the book. It's this amazing, ongoing process of refinement. Think about it like this.
Every generation of scientists is building on the work that came before. They take an incredible piece of work, like the Schrödinger equation, which is like a magnificent first draft, and they add new chapters, they clarify things, they add new details. It's not about throwing out the old rulebook. It's about making it better, stronger, and more powerful. And that just leaves us with this incredible, thrilling question. I mean, these scientists took a swing at one of the most fundamental equations in all of physics. It just goes to show you that even our most solid, time-tested laws might not be the final word. They might just be the current draft, waiting for the next person to come along and write the next chapter.